All right, so today we've just done our review of addition chemistry, which is kind of the opposite of what? Elimination, that's right. So a lot of stuff is very similar, right? We're going to talk about oxymercuration-demercuration, which is what Allison referred to, right? And it's nothing more than adding water across a carbon-carbon double bond in a Markovnikov fashion, okay? But it avoids rearrangement, which must mean what?
You get exactly what you want out of it.
Well, that's true, but what must it mean if we're avoiding rearrangement? What can't I have as an intermediate? Can't have a carbocation, because I told you that there's a cardinal rule of carbocations, right? And that rule is that if a carbocation forms and it can rearrange to a more stable one, it will, right? And so if we're avoiding rearrangement, the only way we can avoid that is if we avoid the carbocation altogether. We're also going to talk about hydroboration, this hydroboration oxidation sequence that we talked about on Monday. That's nothing more than adding water across a carbon-carbon double bond, but it's not adding it in a Markovnikov fashion, it's adding it in an anti-Markovnikov fashion. So it allows us to make what we call anti-Markovnikov alcohols. And then we're going to talk a little more about the addition of halogen across a carbon-carbon double bond. Because on the board, I didn't give you any stereochemistry, right? But there is stereochemistry involved. And how those halogens add across that carbon-carbon double bond is very selective, okay? So let's start off by talking about the oxymercuration-demercuration procedure. Okay, it's a two-step method. It's one pot, but it's two steps. And actually on Friday, I'm going to do a demonstration on the oxymercuration-demercuration sequence, because it's kind of cool to watch it, and it's something that we typically don't have you do in the lab. Why would we not have you do the oxymercuration-demercuration? Because you work with mercury, that's right. What do you know about mercury? It's bad? Mad Hatter, that's right. It can, yeah. You can go crazy over it, right? So it's mad as a hatter, that's right. Mercury is believed to be involved in that. But nonetheless, mercury is a very useful element. It is still used, although people are always trying to find ways around the use of mercury because of all the problems that you've just mentioned. What's the largest source of mercury contamination to humans? And why?
That concentrates as it goes up the food chain.
That's true. So little fish are eaten by bigger fish. So is it a problem if we eat little fish or big fish? Big fish, right? So, okay. So where do the fish get the mercury? Industrial runoff? Could be a potential source. There's a much larger source than just industrial runoff, though. But it does have to do with an industry. I don't know about that one. It's possible, I just don't know. How does West Virginia make all of its money? Mining what? Coal. What does coal have to do with mercury poisoning in fish? It is a good question.
There's not just a whole bunch of coal in the ground, there's other stuff around it and with it.
Uh-huh.
So when you take the coal out, you're also taking out all the other stuff and just letting it go into the environment.
How?
Mountaintop removal mining, they just coil it.
What do they do with the coal? Pardon? They burn it. That's exactly right. And coal has mercury in it. Anybody know why coal has mercury in it? Because it's got sulfur, and sulfur likes mercury, right? And so there is mercury in coal. Now, not a lot, but how many tons of coal do you think we burn a day? A lot. That's right. So as coal-fired power plants burn coal, mercury is vaporized into the atmosphere in various species. We're not going to get into that kind of detail. It ends up being precipitated out in rain, which ends up in the ocean, which ends up in the food stream, which ends up in little fish, which ends up in big fish, which ends up in our belly. Okay, so yeah, eating big fish can lead to mercury contamination. Okay? And they taste good though, right? So anyway, this is a two-step process. The first step is oxymercuration, where we're going to react the alkene with mercuric acetate, HgOAC2, which is going to function as an electrophile. If it's functioning as an electrophile, what's its role? Is it a Lewis acid or a Lewis base? It's a Lewis acid. All electrophiles are Lewis acids, right? And we're going to do this in a mixture of THF and water. Okay, what's the THF for, do you think?
To make sure everything's dissolved.
That's right. THF is soluble in water, and the alkene is soluble in THF. So by adding THF, we can ensure that the alkene and the water will dissolve into one another. Okay. And so the first step, here we've got just a generic alkene. We've got a mixture of water, mercury acetate, and THF. And the first step is oxymercuration. So what's actually being added across the carbon-carbon double bond based on that name? An oxygen atom and mercury. Okay? However, that oxygen atom is added as OH. Where does this oxygen atom come from? It comes from the water. That's exactly right. And the mercury comes from the mercury acetate. Okay? This is known as the oxymercuration product. You know that this reaction is over because when you start off, this is yellow. Well, kind of golden, actually. It's kind of USM gold, really. And as the reaction proceeds, this is colorless. So you can tell when the reaction's over very, very easily. Does anybody know what's strange about that oxymercuration product? What's unusual about it that you haven't seen before? You do get a weak acid, that's true. What else?
Not like a ester, but you've got this random mercury in there.
Yeah, you got a mercury in there. I wouldn't say it's random.
Well, not random mercury,
Yeah.
but like we haven't seen it.
You haven't seen that. Okay, very good. But mercury is also bound to what?
A carbon.
A carbon atom. And we haven't talked a whole lot about carbon atoms being bound to a metal, right? These are known as organometallic reagents. Okay? And as time goes on, you're going to learn a lot about organometallic reagents. And in fact, if you go to graduate school, there's entire classes on organometallic reagents. And there are tons of people with Nobel Prizes because of organometallic chemistry. Okay? It's a very, very important field. And so we've just made an oxymercuration product, which is an organometallic reagent. Okay? And of course, we get acetic acid as a byproduct. Okay? First step is over. Is that an alcohol? Have we added water formally across the carbon-carbon double bond yet? No. What do we have to do? And replace it with what? Water? We've already got the OH on there, right? We've got to replace the mercury with what? With a simple hydrogen. That's all we have to do, right? So the second step is known as the demercuration step. And what you do is you use a solution of sodium borohydride in water. Sodium borohydride, NaBH4, is a salt. It is also a reducing agent. It will reduce the mercury off, okay, and replace the mercury atom with a hydrogen, okay? And you get mercury and you get acetate anion. Anybody know anything about the physical state of mercury? That's mercury 0 as it sits on the periodic table. It's a liquid. What else do you know about it? It's a silver. It's known as quicksilver, right? Where do they get the name quicksilver?
No, because they'll be the same.
The thing.
You know,
I don't know what thing you're talking about.
when it flows weird.
Okay, yeah, it flows very quickly, yeah, so quicksilver. Silver by itself is a solid, right? And this looks almost identical to silver, and so they call it quicksilver because it's a liquid, okay? This is a very simple procedure, and the yields are quite high. And it avoids carbocation rearrangements because there is no carbocation in this two-step process, okay? This reaction is carried out in a simple flask at room temperature. That's why I'm going to be able to do this in here as a demonstration for you on Friday. Okay? It takes only a few minutes to do, and the overall yields are usually better than 90%. And the cool thing about it is that when you have the organometallic reagent, the oxymercuration product, everything's in solution. And as soon as you add the sodium borohydride, you see mercury droplets starting to rain out of the solution. That's kind of the cool thing. And as it continues to rain out, eventually it forms a nice little blob of quicksilver in the bottom that you can see. Okay? And so it's a neat little reaction. And so we're going to make an alcohol in class using the oxymercuration-demercuration sequence on Friday. Okay? So let's look at some examples. If we take one hexene and we do the oxymercuration-demercuration sequence. Now, the reason they put hydroxide here, it's not involved in the reaction per se. Sodium borohydride in water is stable only if the pH is greater than 7, so they add a little hydroxide to make it basic. If you add sodium borohydride to neutral water, it slowly decomposes, and so they have to keep it basic. 2-hexanol, 96% yield. Pretty darn good. Is that a Markovnikov addition or an anti-Markovnikov addition? And how do you know that?
Because it's on the slide.
But how do you know that? Don't tell me because I told you. Why do you know that that's a Markovnikov addition of water across the carbon-carbon double bond? Which one got the hydrogen? The more substituted? The least substituted carbon. The one with the most hydrogens, that's right. And the OH went to the one with the least number of hydrogens, or the most substituted, right? So yeah, it's a Markovnikov product. That's the same product that we would get if we took one hexene and reacted it with sulfuric acid and water. Exact same product. Okay? What do you think the product's going to be for this one? Where's the OH going to go and where's the hydrogen going to go? What do you think, Jamie?
OH will go on the one that has the methyl group.
Okay. And the hydrogen will go here? Yep. You'll get 1-methylcyclopentanol out of that reaction. Is that Markovnikov or anti-Markovnikov? That's a Markovnikov product again, essentially in quantitative yield. Okay? Now let's look at this example. Where's the OH going to go? Carbon number 1 or carbon number 2? The OH? Carbon number 2. And the hydrogen's going to go to carbon number 1, right? And we're going to end up with 3,3-dimethyl-2-butanol and 94% yield. This is the interesting one. Because if Nathan came into the lab and he thought, well, I don't want to work with mercury, and so what I'm going to do is I'm just going to do this reaction with sulfuric acid, which is pretty safe overall, and water, he isn't going to get this reaction product. Why? That's right, we're going to get a carbocation rearrangement. So let's walk through the mechanism of this. What's going to happen in the first step? When I have sulfuric acid and water, I can think of that as H+, right? So what's going to happen in the first step? What do you think, Sam? I've got a Lewis acid, right? What's it going to react with? Oh no, we're starting here. This is product. We're not there yet, right? We're not even going to get that product. We've got this plus this to start out with. What's going to react? The pi bond. Why the pi bond? It's the what? It is weak, and it also functions as a what? As a Lewis base. That's exactly right. So the pi bond reacts with H+, and Markovnikov's rule dictates that that goes where? Carbon 1 or carbon 2? Carbon 1. Right? And so I get a, what kind of carbocation? Now what can happen? Which bond is going to rearrange? One of these methyl groups, right, is going to shift. And why does that happen? Now it's a tertiary and more stable, and so my cardinal rule of carbocations comes into play, right? So now I've got a more stable carbocation. Now what happens? I've got a bunch of water around, right? So what does it do? Yeah, it does. Add arrow. There we go. Now what happens? Got a lot of water around, right? And so I end up with that alcohol. It rearranged. I still get an alcohol, but I rearranged the carbons, right? So if this is what Nate wanted to make, this is how he does it. If he wants to make this, that's dead in the water. That's not going to happen. So he's going to have to do the oxymercuration-demercuration sequence. One of the things that frustrates a lot of students about all these reactions you're going to learn is because you sit there and you go, why do I need to know another reaction to do X? It's because it's not always that simple. You need multiple ways to add things across carbon-carbon double bonds because you want to avoid rearrangements. Because maybe you want to add the hydrogen to the least substituted carbon and the nucleophile to the most substituted carbon. Or maybe you want to do the reverse. Okay? And so we need multiple tools in our toolbox. For those of you who've ever worked with tools, how many toolboxes have you ever gone to that just had one screwdriver or one wrench? But screwdrivers, all they do is put screws into something, right? Why do you have to have multiple screwdrivers? Because they're not all the same. That's exactly right. Why do you have to have multiple wrenches? Because not all the same, right? So you're going to have multiple tools in your chemical toolbox to do the things that you need to do as young organic chemists, okay? And this avoids the carbocation rearrangement. So if Terry wanted to make this alcohol from this starting material, this is the way she has to do it. It's the only tool in her toolbox, at least that she knows of right now, that can do that particular reaction, okay? Any questions about that? So oxymercuration does what?
Gives you a high yield of what you want without
Carbocation rearrangement, good yield. What else does it do? Formally, what does it do? It adds what? It adds water across a carbon-carbon double bond, okay? Would we have to do oxymercuration-demercuration with one hexene? Why not?
You already get a good yield of what you want doing it with just sulfuric acid.
Sulfuric acid and water, right? And why do I not have to worry about carbocation rearrangement there?
Because it's already on the tertiary.
Tertiary? Would I get a tertiary carbocation here?
There's nothing that can make it tertiary.
Nothing that can make it more stable, right? So that's fine. We could do the normal water and sulfuric acid. We could do the normal water and sulfuric acid here. Here, this is the choice that we have to use, okay? And again, it is a Markovnikov product, okay? So there is no carbocation intermediate formed during the oxymercuration step. That's just a fact. How is that true, though? What is it about mercury that keeps it from forming a carbocation? What do you know about mercury? Where's it at on the periodic table? And the transition metal, right? Pardon? It is a heavy metal. Yeah, what else do we know? It's got a lot of electrons around it, right? Is it limited to forming 4 bonds like carbon is? It can form a lot more bonds, right? It doesn't have to follow the octet rule, does it? And so if we think about the mechanism of the oxymercuration-demercuration reaction, okay, we're going to see a couple of things. Now, it turns out that when mercury acetate gets dissolved in water, it dissociates. It's an equilibrium reaction, but it dissociates into the mercurinium ion and acetate, kind of like a salt. So the mercury is positively charged, just like Matt just said, right? And so it's going to accept a pair of electrons from the pi bond, okay? And you might be thinking, well, if he pushes the electrons here to H+, how is that different than pushing the electrons to Hg+? Shouldn't that give me a carbocation as well? You would think so, right? It ain't this simple. That's the whole point, right? Just not quite that simple. And in fact, what happens, the mercury will react, okay? But it forms a three-membered ring, okay? It's not as simple as this single arrow, okay? These electrons react with mercury, but mercury has other electrons around with it that react with the other carbon. And you get what's known as a mercurinium ion. The mercurinium ion is a positively charged intermediate, but it ain't a what? Ain't a carbocation. I'm using a little bad language here, right? Ain't. And since, where is the cation character? It's on the metal. It's on the mercury, right? So can it rearrange? No, it cannot, right? It cannot rearrange. And so no carbocation, no rearrangement. Mercury's our savior here, right? So now what happens? Is that the product we got from the first step? What has to happen? I think you said it, Matt. That's the second step. We're not done with the first step yet. Okay, water has to come in and do something, right? Where does the water have to come in? Where does it attack? If it attacked the mercury, I would end up with an HgOAcOH. That's not what we end up. Where does the OH end up? This carbon or this carbon? This one. So since we know that's where it ends up, tell me where water has to attack. It has to attack that carbon. Why does it attack that carbon? Huh? I'm sorry, I didn't hear you. Okay, to open up that three-membered ring. What do we know about three-membered rings? They have a lot of strain, right? Those carbons are sp3 hybridized, right? Do they want to be part of a three-membered ring? No. And so the way that we relieve that strain is to have water function as a nucleophile and attack the mercury ion, okay, at the carbon atom. And so those electrons that are between the carbon and the mercury go to what? As the water comes in, where do these electrons go? They go to mercury, right? And so we have no free carbocation ever in this particular mechanism. Now, let's think a little more deeply about that problem. And we'll just use this as our example. Draw this up here on the board. So we've got mercury acetate that we know forms HgOAc plus OAc minus, right? So we know that we're going to form this three-membered species. That's a G. And now what happens? Oh, we're just in the first step. We haven't done the second step yet. I've got water around, right? I got a lot of water. It could either attack this carbon or it could attack this carbon. And we know it attacks one of them. Which one does it attack? The dotted line or the solid line? The dotted mechanism. Why? True. Why? Why does it attack this one over this one? I would argue, if I was starting out, that attacking this carbon should be a lot easier. There's nothing in the way, right?
But it forms a more stable.
I know. Do nucleophiles like to go after strong bonds or weak bonds? Weak bonds. That must mean that this carbon-mercury bond is weaker than this carbon-mercury bond. Why?
Because the other one has all these other carbon atoms that it likes to hang around with, while the other one is forced
You're close.
to be with this mercury atom that it
You're
doesn't
close.
really bond with.
Since this mercury atom has a positive charge, do you think it's tugging equally on both of these carbon bonds, the electrons? No. It's pulling these electrons closer to it than these electrons. Can you tell me why?
Since there's more carbons surrounding that, that means that
It's more substituted.
it's more substituted, so the
If we're pulling electrons from here closer to the mercury, what's that going to put on this carbon? A negative? If the electrons are going towards the mercury? Kind of a positive, right? What do we call that? Partial positive, that's right. But a partial positive charge isn't a carbocation. So it can't rearrange. But that means that the more substituted carbon can better handle the partial positive charge, right? Because it's like carbocation stability, in a way. Okay? And so that makes this bond stronger or weaker. The weaker. And the nucleophile is a fairly weak nucleophile. Water's not a strong nucleophile, right? So it's going to go after the weakest bond, and that's this carbon-mercury bond. And so in doing so, the hydrogen on water had to go somewhere. It reacts with that to make the acetic acid. That's what we get in that first product. Now, Matt, now what happens? Sodium borohydride, there you go. We're finally at Matt's reaction he wants to do, right? And the sodium borohydride replaces the mercury with a hydrogen atom. I'm not going to go over the mechanism for that because it's actually a free radical mechanism and it's complicated. All you need to know is that the mercury gets replaced with the hydrogen from sodium borohydride, and I end up with my final product, which is adding water across the carbon-carbon double bond without carbocation rearrangement. Okay?
So there's a partial positive on the carbon
Yes,
in the middle, and
there
there's
is.
a full positive charge on the mercury.
Well, that's where the ion really resides, but it's pulling electrons to it to help remove that positive charge, right? And in fact, if I draw this properly, I really need to draw it lopsided, and it's hard to do. But this bond is actually longer than this bond, okay? It's not an equal triangle, okay? So one bond is actually longer, meaning that it's stronger or weaker? Weaker, that's right. And so that's the one that the nucleophile attacks, okay? And that's the mechanism. Rose comes into the lab and she takes isobutylene, which is this. She mixes it with water and sulfuric acid, catalytic amount, and she finds that she only gets this alcohol. And that makes sense, right? Because that's Markovnikov addition of water across a carbon-carbon double bond. Nothing surprising there. That's all she gets. But I told her to make this alcohol, and all I've got is this in terms of organic material for her to work with. I said, take this and make this. Obviously, this route won't work, right? What tool in her toolbox does she have to make this alcohol instead of this one? It's an anti-Markovnikov addition. That's exactly right. So what is the tool in the toolbox to do that? Oxymercuration-Demercuration follows Markovnikov's rule. The hydroboration oxidation sequence is the other tool that she has in her toolbox. She's got 3 tools in her toolbox to make an alcohol right now. She can add water using water and sulfuric acid, which is Markovnikov addition, forms a carbocation and can rearrange. So there are issues. She has oxymercuration-demercuration, which follows Markovnikov's rule but avoids rearrangement. And the other tool she has is the hydroboration oxidation sequence that allows her to make anti-Markovnikov alcohols. She's adding water across the carbon-carbon double bond, but in the opposite way. The hydrogen is actually going to the most substituted carbon, and the OH is going to the least substituted carbon, right? And so that's where hydroboration oxidation sequence comes in. You're going to use what's known as BH3. Now, you never use BH3 proper. We'll talk about the actual reagents you use in just a moment. But what happens is BH3 will react with an alkene to put a hydrogen and the boron across the carbon-carbon double bond in the first step. Okay? What do you know about BH3? Where's boron on the periodic table? It's right there, right? What rule should it be following? The octet rule. BH3, though, how many electrons does boron have around it? It has 6. Boron can follow the octet. It's part of the second period. It doesn't have to, but it's part of the second period. It would like to have 8 electrons around it so it could look like good old neon, right? But it's far enough over that it doesn't have to have. It can actually have 6 electrons around it. So if I take boron and I put 6 electrons around it, it must have a vacant what? A vacant orbital. Does anybody know what that vacant orbital is? Is it a p orbital? Is it an s orbital? It is a p orbital. And so BH3 is what hybridization? sp2. It is sp2 hybridized. And that p orbital is vacant, so it can accept a pair of electrons, right? So that makes it a Lewis. It is an acceptor, so it's a Lewis acid. BH3 is a Lewis acid. And so what's functioning as the Lewis base? The carbon-carbon double bond. That's exactly right. However, interestingly enough, the hydrogen and the boron are added at exactly the same time in the reaction. And so you get syn addition of H and B across the carbon-carbon double bond. And you end up with what's known as an alkyl borane. Now this can continue to react with alkene, but that's not the important part. Essentially right now we've added a hydrogen and a boron across a carbon-carbon double bond. And then when we treat it with hydrogen peroxide and base, we replace the boron with OH, and we get an alcohol. Okay? Where do you all use peroxide? Huh? Skin? Hair? Yeah. So it's a topical disinfectant, right? 3% solution that you can buy at CVS or Walgreens, wherever you do your shopping, right? You might use it to bleach your hair. I don't know that too many people do that anymore, but or using peroxide for it anyway. But it can be used for that. But it's a very good reagent for removing boron from an alkyl borane. Okay, and so you can remove the boron and replace it with the OH group. Okay, so what have we formally done over these 2 steps? We've added water across the carbon-carbon double bond. Okay. Now, you do not work with BH3 for all practical purposes because BH3 is a reactive gas that exists as B2H6, okay? Very reactive, and so what we do is we buy solutions of it, typically in THF. And THF has this oxygen atom with these lone pairs of electrons, so it functions as a Lewis base. It reacts with the Lewis acid, and we end up with what's known as a BH3.THF complex, okay? This molecule is pretty stable, easy to work with. Chemists like to work with liquids and solids. We don't like to work with gases very much. Okay? Gases are kind of difficult to work with. Okay? I can buy this in a bottle. Okay? But what you need to know is that this behaves like BH3 in solution. Okay? So on an exam, I could write BH3. I could write B2H6. I could write BH3.THF. I could write BH3.DMS. There's also a dimethyl sulfide version of this. But you need to know, regardless of which one I write, they're going to behave like what? BH3. They're going to react like BH3. Okay? So what happens in the first step is the hydrogen and the boron are delivered at exactly the same time through a transition state that looks like this. Okay, it's called a four-centered transition state. And you end up with syn addition of the hydrogen and the boron. What do we mean by syn addition? From the same side of the alkene, right? So there's going to be some stereochemistry there. Okay? Now, it turns out that once you form the alkyl borane, it can react again with more alkene to continue on to form a trialkyl borane, and that's okay. Ultimately, you'll remove the boron from the organic molecule. So technically, how much borane do I really need for every mole of alkene? What's the stoichiometry? One to three. That's right. What's the 1 and what's the 3?
1 BH3
For every 3 moles of alkene. That's right. So technically, we only need a 1 to 3 ratio of borane to alkene to get this reaction to work. However, in practice, in the actual laboratory, people typically use at least a 1 to 1 molar equivalent because you can never be sure of how pure your borane is because it's highly reactive. Okay? So we typically use it in excess. Okay? So if we look at a situation where we have an alkene that's not symmetrical, right? We have a least substituted carbon and a more substituted carbon of the alkene. The BH3 in theory could add in 2 ways. It could add where the boron goes here and the hydrogen here, which gives this one, or the opposite, where the boron comes here and the hydrogen goes here. We do not observe this particular product. It's this way. And so we've added the hydrogen to which part of the alkene? The more substituted, which is exactly the opposite of Markovnikov's rule. And the reason is because the borane, as it comes in, it wants to get away from this sterically crowded carbon. Okay? That's the easy explanation for it. And so the boron will go to the least substituted carbon, and the hydrogen will end up going to the more substituted carbon. And then when we knock this guy off with OH from the hydrogen peroxide and base, what happens? OH bonds there. And so we end up with what looks like the addition of water in an anti-Markovnikov fashion. Okay? And it works pretty well. It's a 2-step sequence. This is the more stable transition state, because even though the transition state is happening at the same time, this carbon's going to take on a partial positive charge because the boron's taking on a partial negative charge. Why is it taking on a partial negative charge as it reacts? It's getting more electrons. BH3 is neutral, right? And as it reacts with the pi bond, electrons are going to it, so the charge has to become somewhat negative, right? And so what's giving up those electrons? The pi bond. And this carbon is actually more able to handle that partial positive charge. Am I forming a true carbocation? So do I have to worry about rearrangements? No. Okay? And so this is why it adds in the way that it does, and this is the product that we get. This is 100%, people. This isn't 90 to 10. This isn't 85-15. That's all you get. It's that good of a reaction. Okay? It's that regioselective. Okay? And then in the last step, when Matt throws in his hydrogen peroxide and base, the boron gets removed and replaced with OH. And the cool thing about this is we get retention of configuration. Now, why that happens is the purpose of a graduate course. There's some interesting rearrangements that go on. But what do I want you to know? It's retention of configuration. So if this is R or S, I haven't really sat and figured it out yet, it's going to be the same in the product. We do not undergo an inversion, okay? And so it's kind of an interesting mechanism how that happens. Okay? What question?
Okay, so look at the last example you gave, this change from BH2 being an OH. Where does the hydrogen go from the hydrogen peroxide? You just put the OH in, because you got the same hydrogen before.
It's actually not the OH it's the hydrogen peroxide that's making the alcohol, actually. So again, that mechanism's a little more complicated than what I want to go into with you all. Okay, that's more of a graduate level, but it's actually the base reacts with the hydrogen peroxide, and it's the hydrogen peroxide anion that displaces the boron. It's a fairly complicated mechanism.